Imagine two particles, created together, then separated by an enormous distance. One stays near Earth, the other travels across the solar system. Nothing physical connects them anymore. No wire, no signal, no visible link of any kind. And yet, if you measure one particle and force it into a definite state, the other particle instantly takes on a matching state of its own. Not a moment later, not after some delay while information travels between them. Instantly, as if the space separating them did not matter at all. Einstein called this spooky action at a distance, and he did not mean it as a compliment. He believed it exposed a flaw in quantum mechanics, a missing piece that, once found, would restore a more sensible, more classical universe. Instead, decades of experiments have shown that Einstein was wrong about the flaw and quantum mechanics was right about the spookiness. This is not a trick of language, and it is not science fiction. It is one of the most rigorously tested phenomena in modern physics, and it forces us to reconsider what it even means for two objects to be separate. Here is the real question this video is going to answer. Can two distant particles behave as one physical system in a way that classical physics simply cannot explain? By the end of this video, you will understand why entanglement is not a hidden message traveling faster than light, why Einstein's most famous objection to quantum mechanics was tested directly and failed, and what this reveals about the deep, uncomfortable difference between how the universe actually works and how our intuition insists it should work. Let's start with why this question matters beyond pure curiosity. Quantum entanglement is not a curiosity confined to physics journals. It is the working principle behind quantum cryptography, already used to secure real communication networks. It is the foundation of quantum computing, a technology actively being built by governments and corporations around the world, specifically because entangled particles can process certain kinds of information in ways that classical computers fundamentally cannot. Understanding entanglement is not just about understanding a strange experiment from the 20th century. It is about understanding a resource that is actively reshaping technology in the 21st. Before we get to what entanglement actually is, we need to be honest about the intuition that makes it so difficult to accept. Most of us grow up assuming that objects have their own independent properties, existing whether or not anyone measures them, and that separate objects, once separated, stay separate. If you have two coins in two closed boxes and you carry one box to the other side of the planet, common sense tells us that each coin already has a definite state, heads or tails, the entire time, regardless of when or whether anyone opens the box to look. Opening one box and seeing heads tells you nothing new about the other coin. It simply reveals a fact that was already true. This intuition is called local realism, and it rests on two separate assumptions that feel so obvious we rarely notice we are making them. The first assumption, realism, says that physical properties exist independently of measurement, that a particle has a definite spin, position, or state, whether or not anyone is looking. The second assumption, locality, says that no influence can travel between two separated objects faster than light, so what happens to one object cannot instantly affect a distant object. Together, these two assumptions form the backbone of how classical physics understands the world, and they match everyday experience so completely that questioning them feels almost absurd. Quantum mechanics, however, makes a very different set of predictions. To understand why, we need one careful, precise idea, and we need to distinguish the metaphor from the actual physics clearly. A useful way to picture entanglement is to imagine two particles that are, in some sense, describing a single shared story rather than two independent ones. But the picture is only a metaphor. What the physics actually tells us is this: when two particles become entangled, The quantum state describing them together cannot be broken down into two separate independent states, one for each particle. Mathematically, the system exists as a single unified description, even though the particles themselves might be separated by any distance at all. This has a strange consequence. Before measurement, neither particle individually has a definite property, like a specific spin direction. What exists is a set of correlations, precise rules about what the results will be if both particles are measured, even though neither result is fixed in advance for either particle alone. When you measure one entangled particle and get a specific result, the state of the other particle becomes correlated with that result immediately, no matter how far away it is. This is the phenomenon that unsettled Einstein so deeply. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper designed to expose what they saw as an incompleteness in quantum mechanics. Their argument, now known as the EPR paradox, went roughly like this. If measuring one particle can instantly determine a property of another distant particle, then either some influence is traveling faster than light, which would violate relativity, or the particles already had definite predetermined properties all along, hidden from quantum mechanics, but real nonetheless. Einstein strongly favored the second option. He believed quantum mechanics was an incomplete description of a deeper, more classical reality, one where particles carried hidden properties, sometimes called hidden variables, that simply hadn't been accounted for yet. In Einstein's view, the spookiness wasn't a fact about the universe. It was a gap in our understanding, waiting to be filled by a more complete theory. For nearly 3 decades, this remained a philosophical disagreement rather than a testable question, because it wasn't obvious how you could experimentally distinguish between hidden, predetermined properties and genuine, non-local quantum correlations. That changed in 1964, when physicist John Stuart Bell developed a mathematical tool that transformed the debate from philosophy into experimental physics. This is the moment of change in our story, the point where an entire philosophical disagreement became something you could actually test in a laboratory. Bell showed that if Einstein was right, if particles carried hidden, predetermined properties established locally at the moment of their creation, then the statistical correlations between measurements on entangled particles would have to stay below a specific mathematical limit, now known as Bell's inequality. But if quantum mechanics was correct, with its full non-local correlations, those same statistical correlations could exceed that limit. This gave physicists a precise, quantifiable question to test. Does the universe respect Bell's inequality, the boundary predicted by local realism, or does it violate it, as quantum mechanics predicts? Beginning in the early 1970s and continuing with increasing precision through the following decades, physicists built experiments specifically designed to test this question. John Clauser conducted early versions of these experiments in the 1970s. Alain Aspect, in the early 1980s, refined the experimental setup significantly, closing some of the loopholes that skeptics pointed to as possible explanations for the results. And in 2015, teams led by physicists including Ronald Hansen conducted what became known as loophole-free Bell tests, closing essentially every remaining gap that could have allowed a classical local explanation to survive. In 2022, Clauser, Aspect, and Anton Zeilinger were jointly awarded the Nobel Prize in Physics specifically for this body of experimental work on entangled photons and the violation of Bell's inequalities. The result, across every properly conducted version of this experiment, has been consistent. Bell's inequality is violated. The correlations between entangled particles exceed the limit that any theory based on local, predetermined properties could produce. This means Einstein's specific proposed resolution that quantum mechanics is incomplete because particles secretly carry local hidden variables has been directly ruled out by experiment. Whatever quantum mechanics is describing, it is not simply revealing gaps to be filled by a more classical theory underneath. The correlations themselves are more than classical local physics can account for. Now we arrive at the deepening, the part where we need to explain carefully what this does and does not mean, because this is exactly where popular explanations of entanglement tend to go wrong. The violation of Bell's inequality does not mean that information travels faster than light between the two particles. This distinction matters enormously, and it is worth being precise about it. Here is why no usable information travels faster than light, even though the correlations themselves appear instantaneously. When you measure an entangled particle, you get a result, but the specific result you get on its own is completely random. You cannot choose what result you will get, and therefore you cannot use your measurement to send a chosen message to the other location. The correlation only becomes visible and only becomes meaningful when someone compares the results from both locations afterward, and that comparison requires ordinary communication, traveling at or below the speed of light, through a phone call, a radio signal, or any conventional channel. Without that classical channel of communication, the distant experimenter, looking only at their own particles' results, sees nothing but a string of random outcomes, indistinguishable from pure chance. The strange non-local correlation is real, but it cannot be harnessed to send a signal faster than light, which means special relativity remains fully intact. Nature has found an extraordinarily strange way to respect the speed limit on information, while still allowing correlations that classical physics cannot explain. So, if it isn't a faster-than-light message, what exactly is happening? This is where physicists distinguish carefully between three different things: evidence, interpretation, and speculation. The evidence is unambiguous. Entangled particles exhibit correlations stronger than any local, classical theory can produce, confirmed repeatedly through loophole-free experiments. The interpretation of what this means about the underlying nature of reality, however, is where genuine ongoing disagreement exists among physicists. Some interpretations, like the Copenhagen interpretation, suggest that particles simply do not have definite properties until measured, and that entanglement reflects a genuinely non-local feature of quantum reality itself, one where separated systems can share a single, unified quantum state despite spatial distance. Other interpretations, like pilot wave theory, propose that particles do have definite positions at all times, guided by a non-local wave that connects distant particles instantaneously, preserving determinism but sacrificing strict locality instead. Still, other interpretations, like the many worlds interpretation, avoid the non-locality question entirely by proposing that all possible measurement outcomes occur, each in a separate branching version of reality, with entanglement emerging naturally from the mathematics of these branching universes. Physicists have not reached universal agreement on which interpretation, if any, correctly describes the deeper reality underlying these correlations. What every mainstream interpretation must account for, however, is the same experimentally confirmed fact. Local realism, in Einstein's original sense, cannot be the whole story. This is the second turn in our understanding, the moment where entanglement stops being just a strange laboratory result and starts revealing something genuinely deep about the structure of reality. Entanglement forces us to reconsider the assumption that separated objects must always have independent, individually definite properties. In a deeply entangled system, the properties belong to the system as a whole, not to each particle individually, even when that whole is spread across enormous distances. Separation in space, Something we intuitively treat as the most basic form of independence does not automatically guarantee independence at the quantum level. This has moved well beyond a philosophical curiosity into practical technology. Quantum key distribution uses entangled photons to detect eavesdropping on encrypted communication, because any attempt to secretly measure the particles disturbs the delicate correlations in a detectable way, something impossible to achieve with purely classical signals. Quantum computers use entanglement between qubits to perform certain calculations exponentially faster than classical computers, specifically because entangled qubits can represent and process combinations of information in ways that unentangled classical bits cannot. In 2017, Chinese researchers demonstrated entanglement-based quantum communication between a satellite in orbit and ground stations separated by over 1,000 kilometers, using entangled photons to establish a secure cryptographic key, proving that these effects remain intact even across genuinely vast distances, not just within a single laboratory. Let's bring this together into the insight this entire video has been building toward. Entanglement does not mean the universe secretly sends messages faster than light. It means that our intuitive assumption of local realism, the deeply ingrained belief that separated objects must carry independent, predetermined properties, does not hold at the quantum level. Nature respects the speed limit of light for usable information, while simultaneously exhibiting correlations that no theory built purely on local, hidden properties could ever reproduce. Einstein was searching for a hidden layer of classical determinism beneath quantum mechanics, a layer that would make the spookiness disappear. Bell's mathematics and decades of increasingly precise experiments closed that door. The spookiness is not a gap in our knowledge waiting to be filled. It is, as far as our best experiments can tell us, a genuine feature of how reality actually operates. There is one more distinction worth making carefully, because it separates good popular science from the kind that quietly slides into myth. Entanglement is often described using the metaphor of two magic coins, linked so that flipping one instantly determines the other, no matter the distance between them. This picture captures something true about the correlation, but it fails to capture something essential about the quantum state itself. Classical coins, even magically linked ones, still have a definite face at every moment, heads or tails, whether or not you look. Entangled particles, by contrast, do not carry that kind of definite pre-existing value before measurement, at least according to the standard mathematical framework of quantum mechanics and the experimental violations of Bell's inequality. The coin metaphor is useful for a first rough intuition, but it should never be mistaken for a literal description of what an entangled quantum state actually is. It is also worth being honest about a common misconception that spreads quickly whenever entanglement reaches popular culture. The idea that entanglement could be used for instant, faster-than-light communication, perhaps even for time travel or signaling into the past. This idea appears frequently in science fiction, and it is directly ruled out by what is now called the no-communication theorem, a mathematical result showing that no operation performed on one half of an entangled pair can produce any detectable change in the statistics observed at the other half, unless the classical light-speed limited results from both sides are later compared. No matter how cleverly an experiment is designed, a person holding only one entangled particle, with no access to information about what happened to its distant partner, will always see a sequence of results indistinguishable from ordinary randomness. The entanglement is real, the correlation is real, and yet it remains provably unusable as a signal. This is not a technological limitation waiting to be engineered around. It is a mathematical consequence built directly into the structure of quantum mechanics itself. The deeper lesson here connects directly to the question we explored in the previous episode of this series. Just as gravitational time dilation revealed that time was never a universal independent backdrop, but a local geometric quantity shaped by mass and energy, entanglement reveals that separateness itself, the assumption that distant objects must have fully independent properties, is not as fundamental as classical intuition insists. Space, distance, and independence, three things we treat as almost self-evident features of reality, all turn out to be more subtle and in some ways more fragile than everyday experience would ever suggest. It is worth pausing here to clarify one more distinction, because entanglement is frequently confused with a related but different quantum phenomenon: superposition. Superposition describes a single particle existing in a combination of multiple possible states at once, before measurement forces it into one specific outcome. Entanglement, by contrast, describes a relationship between two or more particles, where the combined system cannot be described as separate, independent states, even if each individual particle, considered alone, might appear to be in a kind of superposition. A particle can be in superposition without being entangled with anything else, and two particles can be entangled with each other, while each one, considered in isolation, has no well-defined state at all. Superposition is about possibility within a single system. Entanglement is about the relationship, the shared structure, connecting multiple systems together. Confusing the two often leads to the popular but inaccurate claim that entanglement is simply many superpositions happening at once. The mathematics and the physical implications are meaningfully different. This raises a further question we will explore in an upcoming episode of this series. If the universe itself is expanding, stretching the very distances that separate galaxies from one another, what exactly is expanding, and is there anything for it to be expanding into? That question will take us from the strange connections between individual particles to the largest possible scale, the shape and growth of the universe as a whole. This has been Planck's Edge. Thank you for stepping past the edge of what you thought you knew about separation, distance, and reality itself.